Hello. Today is New Year's Eve, 2016, December 31st, Saturday. Okay, so, alright. I'm going to tell you why I didn't build a show drive this year. Let's go ahead and open up Firefox. Okay. So, camera's so close. Okay, let's just go ahead with it. Okay, so, switch hands. So this is the cell phone here. I've got the Media Avenue showing on here. And I've spent some time working with 3D animations to help depict the show drive. Now, the reason why I'm going to be using 3D animations, it's not so I can Photoshop the show drive working. It's because when the show drive works, I need to be able to clearly convey the reason why it works and where the energy comes from. And there's, it's not one of those things that has a preset order by which you start with one element to the next, because it's like a three-dimensional object, and unlike a two-dimensional thing or even a one-dimensional thing, there isn't really one way to start explaining it. So I want here's an example of why this is so important. In fact, I have some computer animations, some computer animation videos from other people put on this website of S.H.O.WIKI. And there's one of them, for example, classic physics education videos. This one's a really good one.
And that work started with the fact that electric current flowing through a long straight wire produces a magnetic field that circulates around the wire. But how does the strength of the field depend on the distance from the wire? If a tiny segment of electric current could exist, it would produce a magnetic field proportional to the inverse square of the distance. The direction of the field is related to the direction of the current by the right-hand rule, or the vector cross product. The field would be biggest when the current segment and distance vector are perpendicular. But electric currents can never exist in tiny segments. So any real magnetic field must be found by adding up or integrating the contributions due to each segment of a flowing current. The field, due to current flowing in a long straight wire, is always perpendicular to the wire and decreases as the inverse first power of the distance from the wire. The net result is a field that goes in circles. The lines of force are circles concentric with the wire, and the field is the same all the way around each circle. On the other hand, if the wire is bent around into a loop, the current flowing through it produces what is known as a dipole field. A helical winding, or solenoid, is like a stack of current loops. It creates a field much like that of a bar magnet. If the solenoid is bent around into a circle, the donut it forms is called a toroid. The magnetic field of a toroid is contained completely inside the windings. There are no field lines out. Therefore, since an electric current is nothing but moving electric charges, it follows then that flowing electric currents apply magnetic forces to each other. currents flowing in the same direction attract each other, and currents flowing in opposite directions repel each other. The magnetic field is both similar to and different from the electric field. In an electric field, no work is done if a charge is moved around any closed path and back to its starting point.
A static electric field.
Therefore, when starting from any point on any path and returning to the same point, the change in electric potential is always zero. Therefore, the line integral of the electric field around any closed path is always zero. This is a fundamental property of electric fields.
For static electric fields. Okay, so basically, all right, so that gives you an idea of what I'm thinking about doing for the S.H.O. drive. So I'm going to do part of it before I build the S.H.O. drive and part of it after. This is a much longer show down here, also on YouTube. Very awesome. And here's a newer type video. Again, very awesome. Okay, no meme pictures yet. Okay, so going on to different page. Okay, so all right. So basically, I'm a kind of a procrastinator. So what I do is I plan to do things, and I don't exactly do it according to plan. And so what I end up doing is I change the plan, and every time I fail to follow the plan, I modify the plan and I do something that I planned. But maybe it's the case that I can't plan everything in advance, and so that's kind of what happens when there's too much to plan. So, that being said, it gives you an idea of what I've been dealing with. Okay. December Avenue. So these are some of the recent videos I've done. This is the most recent one. I have to use Handbrake. Got to thank EV Blog for giving that presentation on how he does his videos. Very awesome. So now I can, it's going to be easier to upload these large videos. Okay, so this has some. Yeah, I got a faster phone now. It's actually a Huawei phone, the big one. I forgot which one it was. Actually, it's over here. All right, Black Friday deal, $50 during Black Friday. It's a Walmart phone. So yeah. It is a Huawei Ascend XT Android phone. Looks kind of like an iPhone. It's cool. iPhone Plus. Hopefully it doesn't gimp out on me. Alright, so anyway. Some of my equations, I'm not exactly sure how this should all work out. I mean, it's still kind of a draft and all. But yeah, I mean, if you didn't see everything, of course, there's the website at over here, right? Okay. All right. So, furthermore, all right. Okay. I'm trying to figure out what exactly is the reason behind the mechanisms. SHO drive's wiki. There is the animation. Visit SHO.WIKI/3D to see the full page version of that animation. But I already got that loaded up here. So shaky. Oh, I don't have that loaded there. Come on, there it is. All right. Now you know it's actually online and not just on some. There we go. As you can see, it works on the phone, which is awesome. And it's HTML5 with WebGL using 3.js. So it's going to be really awesome when I get it all figured out. It's going to be like an interactive version of that video I just showed you. And it will explain a bit more. That's my goal, is to explain a bit more than what these videos already explain. And dealing with things like field densities, torque densities, Lorentz forces acting on magnetization currents and magnets, where does the kinetic energy come from? Why didn't people notice this before? How do you look at different parts of the field in space, different parts in space? What does the alignment or disalignment of these field vectors have to do with anything? What are some misconceptions about electromagnetism? What are the contentious issues? And believe it or not, there's a lot of contentious issues that are discussed regarding how magnetic fields should be represented. In fact, this is what I consider to be an authoritative source on such matters. I'm going to go ahead and tilt this way because it's just too small. Okay, I'm just too shaky. I'm going to use my other hand. All right. Okay, so basically, all right. This is from MIT. It's from Mr. Haas. I believe it's the same guy who used to be Randall Mills's professor, and Randall Mills is now CEO of Blacklight Power, and he's about to release the Sun Cell about next year or so. So this is his teacher, basically. His text or adapted from it or something, but you got to check it out at this website. You can browse the chapters and stuff. Okay. All right. So basically, here it talks about the force on a magnet, and I notice here there's this gradient of the H field, and often enough, people, when they represent a force on a magnetic dipole with magnetic moment M, where's that magnet? Yeah, the magnetic moment M. Magnetic dipole consisting of positive and negative magnetic charges. Okay, so basically, what that's about is there's an issue regarding how, what is the force on a magnet, and there's actually disagreements on how to represent it. So yeah, now I'm kneeling, so it's a little bit easier. It just gives you an idea of what kind of, contentious natures there are about this. But I believe Mr. Haas is the authoritative one on this matter. And he discusses the things called Kelvin force density. That's like Kelvin, named after Lord Kelvin, I would say. Okay, so macroscopic force densities, Lorentz force density, Kelvin polarization force density. That's for electric dipoles. And then he extends that to this. Now, in a lot of cases, what they'll have is they'll have this gradient applying to the dot product of these things here. So instead of the triangle being here, it's going to be to the left of parentheses enclosing these vectors. But this guy apparently knows a bit more about electromagnetism. He keeps the gradient on the H At least that's as far as he describes the Kelvin force density. So apparently this is closer to the truth, taking basically it's the directional derivative of this product as a function of h. So yeah, very different than having the gradient outside the vectors and having the distributed property or whatever. I mean, not distributed property, but anyway. So there it is. The Lorentz Kelvin force densities, and then that's as well. Okay. Anyway, just as a side note, let's just see here. There's gonna be a surprise later. I just noticed the refrigerator at this apartment is called the Kelvinator. So that's just kind of an interesting thing. Okay. Now, here's the S.H.O. drive information here. This is these are the values that I was using, but I made some corrections to them so that I can have these ends stick out to reflect the greater amount of wire that I had used. And so let's go ahead. That's that. I've discussed that before. All right, so this is something I just did a few days ago. You can see my name. It's also that. Okay. So anyway, flux linkage, magnetic flux linkage, reduced voltage, currents, work and power. So these are like over here. These are related to the co-energy. Let's see as this diverges. Okay, so just to give you an idea, and there's some propagation error. I haven't quite figured out why it's appearing, so I have to use this to calibrate it, use the trend line, try to straighten it. Okay, so I don't think there's much time for that right now. Okay, so this is our S.H.O. drive animation rendering on the local host here, a WAMP server. That's WAMP server. Just to give you an idea. Okay. There it is. WAMP server 64. Okay. There's the S.H.O. drive logo. Oh dear. Okay. Let's put this back. All right. And this is the code for it. Not an octopus, so there we go. Heptapod or whatever. Okay. 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 Let's see, what else? Okay. Alright, so my side project here